Hello everyone, welcome to week 8, and today we're going to get stuck into some hashing, so let's get into it. Make me small, there we are. Let's get into the lecture. The first thing to say is that, most importantly, there is no lecture this Friday. Okay, no lecture this Friday, and nor on this Monday, so you guys get an extra big long weekend. There is unfortunately a deliverable due this Friday, which has two components. And the reason why it's due this Friday, I think I mentioned this last lecture, the reason why the deliverable is due, let me just check the audio is working here. Yep. The reason why the deliverable is due this Friday is because the Monday is a public holiday, so we've brought it forward. The bad news is it's earlier. The good news is you get a long weekend without a deadline looming over your head. And it's not a major deadline. So the two main things there, you've got to do a code review. This is an important thing you need to learn. Code reviews are just a fundamental part of software development in practice. So when you work in any organization, whether it be an open source organization or a big industrial organization, the way you integrate code into a code base these days is that you submit your code using one or other technique or mechanism, and people have to review it before it gets incorporated into the code base, and that's a code review, and different people review it according to which code you're making changes to. And that's a process we use in my lab for my the research projects I do with my PhD students, and that's a process that also gets used in large companies, and that's the sort of thing I did when I was at Google. So you're going to have to do a little code review. That means looking at someone else's code, and then you also have to do, and each one of you does that individually. And also there's a group task where you have to get a jar file working. This is really important. It should be really simple, and so try and do this early on. And you can ask for help on Piazza or in your lab or at the one-to-one consultation sessions. But it's really, really important that you've figured out how to make your assignment work with the jar file. There are instructions there. And it should be easy, but if it isn't, now's the time to find out, because when the deadline comes for the whole assignment later on, you get marked on what's in that jar file, and if you can't make a jar file, then you're in big trouble. So getting the jar file working now is a great idea. And all right. Okay, I think that's about it. Let's move on then. Now, as I said on Piazza, this is a fun lecture, I think, because we're moving away from stuff like syntax into more deeper concepts, and ones that I think are interesting. And this one that we're going to do now is about hashing. We're going to use hashing all through today's lecture, and we're going to start off by looking at hash functions. Okay, and some people think, oh, this is really hard. It's not hard. You all of you understand this stuff. You just may not realize it yet. Okay. So what is a hash function? Now, before I go any further, I want you to imagine that we're back on campus, and I want to run a game thing for the whole class, okay? And you guys always come to class. Everyone comes every week to class, every lecture to class. Now, what I want to do, this is a problem I want you guys to try and answer on the chat. What I want to do is I want you to think about, I give you a problem. My problem is I want you to split the entire class into two teams, okay? Two teams. I'm going to ask you later to split it into more teams, like 10 or 12. But for now, two teams, okay? I want you to split the class into two teams, all right? Now, the trick is there's some catches, okay? So you can think about how you do that at school or whatever. You might have just said A, B, and number everyone off, right? The problem is I want the exact same teams the next week. Okay, I want people to be in the same team. So if a student shows up one week and the next week, they always go to the exact same team. So if you're going to go 1, 2, odd, even like that probably won't work, because that'll depend on what order the people come at you, right? So what I want is a way to split the entire class into two teams that are approximately equal in size. They don't have to be exactly, but approximately equal in size. And I don't want you to have to remember, okay? So I could say, odd, even, and say, don't forget, next week you're odd, for the remainder of the semester you're on the odd team and you're on the even team. But you guys will forget, right? So it'll all get messed up. So I want something you don't need to remember anything. So no need to remember anything. And I want to be the same every week. And the same every week is what we call in computer science deterministic. Has anyone got a suggestion on the chat as to how we're going to do this? Okay. A suggestion. How do we split the entire class into two groups where the same group, you guys end up in the same groups each week, each lecture. You don't have to remember anything. And the teams are approximately equal in size. Perfect. Shuoxin said UID. Exactly. What are we going to do with the UID? I've got a UID. You all have a UID. Okay, he's got a great idea. Odd or even. Yeah, perfect. Yeah, exactly. So he said on the chat here, we're going to use UIDs and to decide if they're odd or even. Okay, that's a fantastic idea because you all carry your your student card. Okay, so and you can just look at that last digit and say, is this an even or an odd? And it's probably a fair guess to suggest that the whole class is very roughly distributed, roughly half odd and roughly half even. So that's a perfect idea. Okay? Now, someone else suggested last name. We're going to come to this later in the lecture, actually. It's a great suggestion. It's the last. Can anyone see a problem with using last name? It's a great idea, but there is an interesting problem here. Okay? Well, you'd have to do it carefully. I guess that's the answer, Victoria. You have to do it carefully. Why? Why do you have to do it carefully? The answer is they're not evenly distributed. Our last names, this event didn't start on MS Stream. Man, it's a pain in the neck. Okay, start event. Sorry. All right, MS Stream's up and running too now. Okay. Yeah, Ben pointed out that there are multiple same names. People have their same last name. That could be an issue. It could mean that the things are lumpy, but also people's names are not evenly distributed across the alphabet. Okay. Now, okay, all right. So a little while ago, someone had a great idea of using the UID, and they said we can do odds and evens. Now, let's say we want to move from having some massive game with 2 teams. I want to move to a basketball tournament, so I want 20 teams of size 8 or whatever. Okay. So if we have, say, 20 teams, say I want to split the class into 20 instead of 2, what do we do? I've had a green screen for a while. I just have not had time to mess around and make it work, and it's still not perfect. But anyway, the question is, I want 20 teams. I want 20 teams. What am I going to do if I've got 20 teams? Maybe Shuoxin, who said odd and even, can generalize his answer from, or their answer from odd and even. How do we generalize that idea from odd and even to 20? Yeah, Adam had a great idea there. Okay, so we could do something like so what odd and even is doing, right? Think about what odd and even is doing. That's taking a number, which is basically your UID, and they're looking at the very last digit and deciding if it's odd or even, right? And if you think about it mathematically, that's basically a remainder operator. If you divide by 2, is the remainder 0 or 1? Okay, if you divide any number by 2, then the remainder will be either 0 or 1. That's integer remainder. Okay, and what Adam has suggested here is we do integer remainder with 20. Okay, and if we do integer remainder with 20, we're going to get numbers between 0 and 19. Okay, and that will give us our 20 teams. Okay, and if our student IDs are reasonably distributed, that should work. Of course, they may not be reasonably distributed, and we'll find out. But if they were, that would work fantastically, and that is exactly the idea. Now, what I want you all to do is to remember this. Remember the basketball. Remember the game. Remember the suggestion from Shuoxin and Adam about using the UID. And if you've done that, you've got hashing. Okay? That is really what hashing is all about. If you can remember that, then you've got the key ideas of hashing. So it's really not that difficult. And these are concepts that everyone probably has lurking in the back of their head. They've just never had it formalized in front of them. So let's move on and make it a tiny bit more formal. Okay, what is a hash function? A hash function is a function that maps a key to a value, okay, within a prescribed range. And it's deterministic. So let's just see those points. It's a function, there's a key, there's a value, a prescribed range, and it's deterministic. So let's just think through the basketball example and, okay, so what's the function? What's the function? The function's on the chat right now. It's UID integer remainder 20. So that's the function, right? What's the key? The key is the thing you put in k into the function, and the key in this example is the UID. Okay? The prescribed range, to a value, what's the value? The value is going to be a number from 0 to 19, which is your basketball team. Okay? 0 to 19. That's the value. What's the prescribed range? 0 to 19. That's the range. We said we've got exactly 20 basketball teams. So we need this function to give us a value in that range. Okay? And above all, the hash is deterministic, which means that each week you're going to get the same teams. The same people will go in the same teams. If someone shows up each week, they're always going to go to the same team. Because, why? Because their UID doesn't change, right? At least we're going to assume the UIDs don't change, right? So if your UID doesn't change, we have a deterministic hash, right? Whereas if I had the thing I started off with and just said odd, even, or, 1, 2, 3, 4, that could be different each week because it would depend on what order you walked in the door, right? If I just numbered everyone off when they walked through the door, then each week would have different teams, okay? Which could be a good thing, but it wouldn't be deterministic, okay? Whereas if we use the UID, we get the same teams every week, okay? And these are the properties of a hash function. Let's just go through them one more time. A function, we see that on the chat right now. That's UID integer remainder 20. That maps a key. The key is the UID. To a value, the value is your team, so 7 or something. Within a prescribed range, the range is 0 to 19. It's deterministic, meaning that we're going to get the same answer every time we do it, okay, for a given UID. All right, so that is a hash function. So how do we choose a good hash function? This is a really interesting question, and we're gonna look at this really closely soon. Okay, how do we choose a good hash function? And the answer to that is try and visualize a histogram. You all know what a histogram is, like a bar chart. Imagine we had a bar chart, and we had a bar chart which the height of the bar was the number of people on each team. What would a good hash function give us? How can someone write in the chat, what would a good hash function look like for our basketball teams? We're going to have 20 bars because there's 20 teams. And each bar is going to be the height of the number of people in the team after we've done our hash function. How do we know if we've got a good hash function? What would the bar chart look like if it was good? Or conversely, what would it look like if it was bad? All bars the same length, right? Or everything's the same height. If everything was the same height, you've got a fantastic hash function because it means that you've distributed them evenly within the range of the hash. Distribute them evenly, okay? So this is how we describe a good hash function. You distribute things evenly, okay? Evenly distributed, right? It would look like the stock market if it was bad, exactly, all right? So it'd be all over the place, all right? And we're going to look at this really concretely later in the lecture. All right, time for the mini quiz. Let's do that. There you go. You should be able to see the mini. Oh, no. There we go. You should be able to see the mini quiz now. And then let's move on. So the last unit we just did, C02, is very, very short, and it looked at basically the theory of what is a hash function. Okay, what is a hash function? You all should know what a hash function is, and if you've forgotten, go back and look at what we just did in the last 10 minutes. Okay, that's a hash function. Now we're moving on to look at applications of hashing, and I want to start with the story. So when I was an undergrad, I went to UNSW, and I stayed in a residential hall, which is a ton load of fun. Okay, and we had about, I don't know, 250 people in the hall, in the residential hall, and we had lots of really good parties and all that sort of stuff. It was really good, and we all lived in there, and we all had dinner together. It was a catered hall, and it was a long time ago, of course, so you can imagine like Hogwarts or something, right? The big dining hall, olden days. So imagine this, right? And one of the things that happened back in those days is that we corresponded with our parents via paper and ink, right? We wrote letters, okay, back in those days. In those days, my folks were living overseas. They were in the Philippines, and my mom used to write to me every week, right? Now, we used to get mail in this residential hall, and so and it was a big hall, so the post office would come with a humongous bag of mail each day, every day, probably about 11 o'clock in the morning. And then we'd all want to see, when we came to lunch between lectures, we'd all want to see if we got any mail, right? Everyone wants to see if they got any mail. And so now think about how they might distribute the mail in this big residential hall. How would you do it? You've got a pile of letters. There's a good pile of letters. And you want to distribute to all the 250 people, okay? So one approach might be get all 250 people line up in a big long line and then just dump the bag of mail on the floor, and then get everyone one at a time to come to that big pile of letters on the floor and pick out their letter, right? They could do that. That would not be an optimal strategy, but that would work, right? What would have to happen? Each person would walk up to that giant pile of mail, and they'd look through all the letters one by one and find out if any of them had their name on it. Okay, that's not what we did. Actually, we had something slightly better than that. Okay. What we had is what we call pigeonholes. Pigeonholes. I mean, a little wooden box. Okay, and we had about 26 of them, right? And yeah, we had one basically for each letter of the alphabet. And like Victoria said earlier, we can hash them by hashing. I've already given it away. We can put the letters into the pigeonholes according to people's last names. Okay, so we had roughly 26, and we had pigeonholes with letters on them. And then when it came lunchtime, all I had to do is go and look at the pigeonhole which had B on it, and then I could look through there. Now, what would I find in that pigeonhole? Well, how many letters would be in there? Well, it could be 0, but it could be quite a lot. Okay, because it could be that there was lots of people whose last name started with B in my hall. There could be. And what happens then is I've got to look through all the letters in that pigeonhole. Now, going back to my question earlier about the hash function, if everyone in the hall's names were pretty well evenly distributed across the alphabet, what you'd see on average is about the same number of letters in each pigeonhole, except for the ones which had people who were really unpopular and didn't get any letters, right? But basically, they would distribute evenly if the names were distributed evenly. But if they weren't distributed evenly, like there were lots of people whose names started with B, then there'd still be quite a lot of letters in B or whatever letter it was, okay? And it turns out that our names are not evenly distributed across the alphabet. But you get the idea. Now, what's going on there? What's going on there is that we are using a hash function, which we just learned about, to reduce a search. Okay, so the example I had, the ridiculous example I started with, is that each one of us would have to look through all of the mail. That's a search, right? And look through it to see if there's one for us. And by using a hash function, that is the first letter of our last name, someone from the office goes and puts them all in these boxes. I still have to search in that box with a B, right? And look in there and see if there's one for me. But the research is hugely reduced. And if the hashing was really good, that is, our names are well distributed, the amount of searching I'd be doing would be approximately 1/26th as much work as if it was just a big pile on the floor. All right? So if you can have that mental image in your head, you will understand what we're going to do in the next major unit, which is A4 actually. It's 2 units away. You'll understand exactly what we're about to do. So have that mental image in your head of the difference between looking through the huge pile of mail for everyone in the hall versus looking just at the box with the letter of your last name on it. Okay? You still have to search, but you have to search through much less stuff. Okay? So let's go on here. The first thing we need to know is that Java offers us something rather helpful. It offers us a hash code for every object. Okay, a hash code for every object. What that means is that for every object, there's a number which does not change, like your UID. Remember, it's like your UID. It's deterministic. It does not change. And it allows us, like the UID, exactly like the UID, to do hashing. Okay, it's like the key to the hash function in the UID example. Okay, and Java guarantees you this. Now, what they don't guarantee you is how well distributed these hash codes are. So if you're building a JVM like I've done, you could legally provide the hash code of 0 for every object, which would be really bad because it would mean it's like everyone having the same UID. It would be really bad, and you would not get good distribution in terms of the histogram. Everything would go in one bucket if everyone had the same hash code. Okay, but of course, most JVMs go to length to avoid that happening, and they try and give all the objects well-distributed hash codes. So the chances are, if you have 2 objects, they'll have different hash codes. They're not guaranteed to have different objects, just like all they're guaranteed is they're well-distributed. Okay, so they're not guaranteed to have different objects, different hash codes, but they're guaranteed to be well-distributed. Okay, that's the point at the bottom of the slide there. Okay, how can we use hashing? One way we can use hashing is to make a hash table, and we're going to do that today. Okay, so I'm going to come to that in great detail shortly, and that is making a map from a key to a value. So you can take a key and you can find a value. Okay, and how do we do that? Well, one way we do that is by pruning a search. If there are lots of objects, there is a chance that 2 of them could have the same hash code. Someone's asking on the chat. So in Java, if there are many objects and you have 2 objects, their hash codes will be different if they're different objects. Okay, so if they're different, If their hash, I'll say this very carefully. If I say this wrong, I'll confuse you. Okay. If I have two objects and their hash codes are the same, what does it tell me? All it tells me is that we don't know that they're different, which is not the same as saying we know that they're the same. Think that through. Okay. If two objects, if two objects have the same hash code, then there's two possibilities. Either it means that it's actually the same object. So if I say A and B and we look at their hash codes and they're the same, that could be because A and B are actually referring to the exact same object. Okay? But it could also be, it's also possible, some probability, that they just happen to have the same hash code. Okay? Now, if we had a really dumb JVM and gave everything the hash code to 0, this would happen all the time, obviously. Okay? So the hash code is just there to help us, and it doesn't have to be well distributed, but it should be well distributed. So it's quite possible that two objects could have the same hash code, even though they're different. Okay? But what's impossible is if I have two references to the same object, every time I look at that object, I'll get exactly the same hash code back. And that's the important property. So if I get different hash codes, then I know absolutely for sure that we're looking at two different objects. That's what I know for sure. Different hash codes tell us we're looking at different objects. Same hash code does not tell us we're looking at the same object. It just tells us that we're not looking at, that we don't know for sure we've got different objects. And there's a subtle difference there. Okay? All right. So pruning a search. I gotta keep moving, guys. So it says here pruning a search. So what does pruning a search mean? If you listen to my example, about the mail in the residential hall, you'll understand what I mean about pruning a search. Okay, instead of me having to look through 250 letters to find my letter, I only need to look through however many are sitting in the pigeonhole which says B on it, which might just be 3 or 4. Okay, so so it reduces the search. So we're pruning a search. Okay, and looking for duplicates. We can also do this the same, because if I've got the same object in here twice, then it was guaranteed to have the same hash code. Okay, if I have two references to the same object, we're guaranteed to have the same hash code. Okay, so and looking for similar values. I'm going to go through very concretely some examples in a minute. Compression. Okay, a hash is typically much more compact than the key. This is interesting. We can use this to compress information. Okay, in an interesting way. I'm going to go through concrete examples of this too. Some of this is a little bit mind-bendy, and it will help if we go through the concrete examples, which I'm going to do in a moment. Okay. And finally, checksums. Checksums can confirm inequality. Now, what I love giving this lecture live, so I'm really bummed that Zoom is not working and that we're not in the same room together. But I would ask you a question. I want you to think of a Boolean. Everyone, I'm going to imagine I'm pointing to one of you. Think of a Boolean, okay? Think of a Boolean in your head. Now, if I look at one of you, look you in the eye, and I'll say, tell me the answer, tell me what Boolean you are thinking of. What Boolean are you thinking of? And you say true, okay? If I say you're wrong, then what do you know? You now know the answer, because there's only two ways a Boolean can be. It can either be true or false. And so if you guessed something and I said that's wrong, then you know not perhaps, but exactly what the answer is, which is an interesting property of Booleans. So if you have a value of a Boolean in your hand and someone tells you it's wrong, then you know precisely what the right answer is, which is a very, very interesting property. It sounds odd, perhaps, or perhaps kind of trivial, but it's actually a really powerful property, and that allows us to do what we call checksums. Okay, and it allows us to have things like error correcting codes in memory. Okay, where the memory can figure out it made a mistake and then fix it. Okay, because if it knows that this bit in memory is wrong and the current value is 0, well, it must be 1. Right? So this is a really, really interesting property, and all this comes down to, it's very, very closely related to what we call hashing. So let's go through some concrete examples. The Lun algorithm, and it's used to check for transcription errors. So for example, in credit cards, some of you may have noticed that we can tell if your credit card is, if you enter a credit card number into an app, into a web page, right? It can tell you if you typed it incorrectly before it sends any data to a server. The reason why is that it uses what we call a checksum. So what it does is you've got all these digits Yeah, Hamming codes are on the screen. That's one of the examples. Okay, Hamming. That's Richard Hamming. There's a photograph of Richard Hamming over there. You can go read tons about Hamming. He's a really, really interesting guy. But let me continue with the Lund algorithm first. So what the Lund algorithm does is imagine your credit card, get rid of that last digit, okay? Get rid of the last digit on your credit card. Each digit is between 0 and 9, right? And then what you can do is you can add them all up. Add up all those digits, okay? So sum up the digits. So the first one might be 3, then you add the next one, which might be 5. So now you've got 8, and so forth and so on and so on, okay? And you do all this stuff, and then just for everything except the last digit, then you get a number, which is the sum of all the digits in your credit card. Okay. Then you take that answer, which could be say 27, right? So imagine you add them all up and you got the number 27, right? Then what you do is you take the integer remainder of that when you divide by 10, which would be 7. Okay. So you take the last digit, 7, and then when you write your credit card number down, you always put that 7 last. Okay. Now, if you make a mistake when you're writing down your credit card number, someone can check by doing that same check and add up all the digits and see if the last one is correct or not. And you'll realize that will, with a very high probability, roughly a 9 out of 10 probability, notice that you made a mistake writing your credit card number down without having to go to the bank and check or anything like that. Okay, so that's a Lund algorithm. Hamming codes, like I said before, can be used to, for example, correct correct an error in memory. If we know for sure that this bit is wrong, and a bit only has 2 values, true or false, and we know this one's wrong, then obviously the right value is the opposite of what it is now. Okay, so if someone says that is wrong and it's 1, then we know the correct value is 0. Conversely, if it's 0 and someone says it's wrong, then we know the correct value is 1. Very neat and kind of trivial idea, but it's very powerful because it allows us to do things like error correcting codes. 2 more great examples. Rsync, this guy Andrew Tridgell did his PhD with me. Look him up. He's an amazing guy. He lives in Canberra. He's one of the great contributors to open source software. There's tons of stories I could tell you about him if we had more time, including how his role in the creation of Git. It's a very interesting story, but one of the things that Tridge did during his PhD, you can actually look up his PhD thesis online and read about Rsync. Rsync is a file transfer protocol which, it's kind of by magic, it sounds like magic. What he can do is, if I've got a giant amount of files on one machine and a giant amount of files on the other machine, which are almost the same, but not quite the same, it can figure out what the difference between this is and this is, and just move the difference. Okay, so I want to update the one over here to be the same as the one over here. Now, the dumb way to do it is to copy all these files over to there, and then you've done it, right? But a more efficient way to do it would be to notice what the difference is between this, and just move the difference. And the question is, how can you do that minimally? And that's actually a really interesting and hard problem. And there's an algorithm, a great algorithm, which is really widely used in lots of software today, that Tridge developed, which uses checksums. In fact, it uses something even more clever than that. It uses what we call rolling checksums to essentially just transmit the data that's different plus these checksums. Okay, it's a very, very cool algorithm. Go look it up sometime if you want. And that's a great example of using hashing. And MD5, some of you heard of MD5. MD5 used to be used for encoding passwords. We don't use it anymore, but it's a way of saying, okay, you type your password in, and then we don't want to record your password in this file because someone could figure out what your password is if they had access to that file. Instead, what we're going to do is take your password and then we'll hash to it. Okay, and then there are a whole lot of things we can move on to from here which go into cryptography, which were not part of this course. We're not going to talk about it any further, but you're very welcome to go and look at that later if you're interested. There's a whole lot of interesting applications here which verge into cryptography. With that, we're going to move on and we're going to do an example. I'm going to publish that poll. There you go, the poll's published. And we're going to write some code. There we go. Where are we? Okay. What I've done here is I have written a very, very simple little demo. And so there's a thing here called a histogram class. It's really, really bad, but it looks just like the histogram I sketched in your mind's eye about 10 minutes ago for saying what the distribution of values is. And then what I've got here, I've got 2 data sets. I've got a whole bunch of given names, a whole bunch of family names, and a dictionary of words. Okay? given names, family names, a dictionary of words, and I've got everyone's UIDs. Not from this class, I got last year's class in there. Okay, but you can see them up here. Family names, given names, UIDs, and a dictionary. Okay, now what we're going to do is, I'll just comment this out to start with. What we're going to do is write some hash functions. And all we need to do is write, the way I've written my thing is it takes a lambda. Okay, so what we're going to do is we've got here a lambda which says take keys and buckets and return. That's your function. Your function, this function here, this is a function written as a lambda expression, and it's a pretty bad function. What is it doing? It's saying no matter what the key is, no matter how many buckets you have, we're going to return 0. This is the really bad hash. Okay, now the buckets in our example is like if that's how many bars there are in the histogram, so it's how many teams there are. So I start off with the example of 2 buckets or 2 teams, and then I move to the example of basketball where you had 20 teams in the class. Okay, so we call them buckets. You often refer in hashing to buckets. So you put things in buckets. Okay, and a bucket looks like a bar on a histogram. So if I plot this, what's going to happen if I say take all those integers, which is everyone's UIDs, and whatever UID you have, I'm going to return the value 0. What's the histogram going to look like? This should be pretty obvious. Okay, let's just run it, and hopefully you've already guessed. I can't hear you, sadly, but if I could hear you, hopefully you'd be yelling out to me and telling me what it would look like. Oops, what happened there? PowerPoint's jumped back up. But there's your histogram. Okay. Can you see the histogram? Let me see if I can move this over. Where are we? No, it's not going to do it. All right. We've got a very bad histogram here. So, okay, so this is an example of a really bad one. We've got everything here is empty, and this one here has got all the values in it. Okay? So there's no scales in this, but that's obviously a really bad hash function. Okay? Now let's go and change this, and I need to stop that program there to get rid of that. And so now let's write a better hash. So what's a better way of hashing from those UIDs into some number of buckets? We've got to write ourselves a hash function. Okay, so let's write one here. Now it was obviously ridiculous. The one I just wrote was a ridiculous one, which is hashing everything to 0. You put everything in one bucket, of course, which is not a good idea. So let's write a different hash, and we can change the color. Change it to another color just so we can put them side by side perhaps. And we'll write a hash function here. Can anyone guess what's a good way to hash them? Someone already said it. In fact, I think Adam said it earlier. Let's just try his function. He already said it. So what was it? Key, integer, remainder. And he said that, right? He actually wrote exactly that in the chat. But we're generalizing it and writing this. Like buckets. Oops, typo. Okay, in the chat, he said key, integer, remainder 20, and in this case we're generalizing. Yeah, exactly. Shuasin said key, integer, remainder buckets. Perfect. Now let's have a look and see how good that is. And the input data set, which is under the hood here, you can go look at the code. I'll push it later. You can look at it. It's reading in all the UIDs in that file over here. Okay, it's just going to read them all in. And if we run this, run it here, what do we get? And that's a much better hash, okay? So you can see there, all the bars are fairly close to being equal, okay? So this is like our basketball thing, right? So this is the basketball teams that we would have got if we took the hash function that Adam had suggested earlier when I was asking you to put everyone in basketball teams. And you can see the smallest of them's maybe this one over here. That's the smallest team, and that's the biggest team. Pretty good for an automatic distribution, right? Pretty good. So that is one hash function. Anyone got another suggestion? That's probably a good enough, one small refinement we could do, I suppose. Just do one small refinement. And that is we could say, change the color here. I'll just quit that. There we go. One small refinement is to say, let's divide the key by 10 first, because actually, I don't know if you know this, but the UIDs also have checksums in them, like the Lun algorithm I was describing for credit cards. Okay, so the last digit, I believe, of your UID is actually redundant. So we can throw away the last digit and we still get a unique UID. So let's see if it gives us a better hash. It may not. Let's just have a look at it. We should get 2 now, light green and a lime green. There we go. And it doesn't look greatly different. Maybe the lime green is actually worse. Oh well. Okay, it was worth having a look at that. But you can see, hopefully everyone here is getting a good intuition for how these hash functions are working, and that drawing them as histograms gives us a sense of how the distribution might work. Now, what I want you to think about right now, I'm going to be doing the coding in a few moments. I want you to think about now how we're going to hash words in a dictionary and people's names. Okay, first names and last names. Notice that the people's names may not be very well distributed. Also, words in an English dictionary, English words are not very well distributed across the alphabet either. Notice that. So have a go writing in the chat a hash function in a moment that we can use for doing words in a dictionary. Okay, so I'll look in the chat in a few moments. In the meantime, I will do this here, and we will, oops. All right, so now let's have a look. We've got another hash function which hashes a string, and it uses this function here. And of course, this is a ridiculous function because it's going to map everything to 0, which is not a great idea, and we should get just what we saw before. All right, see if you can write some code down there, folks. Give me a tiny little lambda expression if you can, so I can cut and paste. Otherwise, I can just type something in. All right, so what we got is exactly what we expected. That's a ridiculous hash function, and we see that that everything went into one bucket. Of course it did, because we made everything be equal to 0. Then we've got family names, given names, and a dictionary. They all looked exactly the same. Okay, so we have three different graphs, because I was doing given names, family names, and dictionaries, and they were all using this silly hash here. Okay, so let's see if we can do better than that. Okay, and is anyone going to type a piece of code here? Let's do something simple. Let's just go, while I wait for someone to do something better, let's go and do something like this. Let's say, change the color, and just say, let's get the first character, say. I'm looking for someone to type some code in there. I mean, I can type code myself, but if you guys, I want you to make a suggestion, or it doesn't have to be syntactically perfect, but just write an expression down there if you can. See if you can write something. What I'm going to do is I'm going to do something like this, just as an example. Looking at the first letter, which is how we hash the mailboxes in the residential hall I lived in. Okay, so what we did is return, and then we do something like this. We say key dot type, man, I'm having trouble with my keyboard again. Move it across, char out, there we go. Char out 0, so it's going to take the first character, right? Key dot char out 0, so that will be a character, and then we can just take the integer remainder of that value in the number of buckets, right? So that will take, it will take some ASCII value for that character at 0, and then just take the integer remainder of the buckets. Okay, so let's just do that and see what we get. Okay, what's happening here? There we go. Okay, good. All right, so let's have a go at this. Hopefully this will be better than our ridiculous one where we just mapped everything to 0. Let's run it. Convert characters to numbers, add them. Oh, add them and divide by 26. Okay. All right. Again, if someone could write code, that'd be cool. There we are. So this is what happens if we just look at everyone's, at the first letter of the word. So this is a dictionary. First letter of the word in the dictionary. First letter of people's family names. And first letter of people's given names. Notice this is terribly distributed. Look, there's one here which looks like it's only got 1 in it or 0 in it. So there's something here which has basically no one's family names look like that. And then there's other ones here and here and here which seem to be really popular. Okay, there's 20 buckets here. It's not 26, so we don't know which letters of the alphabet they correspond to. But you can see there's a terrible distribution. So using the first letter is really not a great idea. Even for the English language, this is the English language now, we see a similar problem. There are some here which don't have very many in the bucket at all. And then true for the given names as well. We've got one here where hardly anyone's given name starts with these letters, and then a lot of people's given names start with those letters. Okay, I don't know what they are, but it's interesting. All right, so now let's go back to here and write something else. Still looks like no one's given me a piece of code. Oh, disappointing. All right, so I'm going to try and do, let's see if I can do what Linda just said there. It's similar to what Adam said. Oh, someone's written some code in. Let's have a look. Liam's put some in there. Okay, so I'm going to put in, let's make this another color. Let's make it purple. And try this piece of code out. All right. Oh, I just remembered that the chat is on a completely different computer to this code thing here, so I'm going to have to transcribe it. I have to literally type it in. See more. All right, I'm going to have to type this in. All right, Cool. I'll do that. I'll go and type in what Liam has put in there, but I need to type it because it's actually a physically distinct computer. So we're going to say int sum equals 0. And then we're going to say for int I equals 0. Yep, okay. For int I equals 0, I is less than key dot length. Yep, I plus plus. And then what we're going to do is say add. Okay, going to add them all up. Sum plus equals key dot charat I. Okay, so we're getting the ith letter. We're going through all the letters in that string, and we're summing them all up, which is what Linda said the same thing. So a number of people are saying similar things here. Now sum will be equal to all that stuff. Then what we can do is we can return the take that sum like that. Okay. Now I've written what Liam has suggested. Let's have a look. All right. And Griffith has got another suggestion, which I'll look at in a second. Whoa. Okay. Great job, Liam and Linda and everyone else who thought of that idea. So look at that. The dictionary's looking superb. Family name's not too bad. Given name's not great. Not too bad either. Dictionary over here. So there's your comparison, folks. Okay. So these ones here are using the hash function of just looking at the first letter. These ones here are adding up all the letters. Okay. And that's obviously much better. And now let's have a look here. Let me look over in the chat. Yeah, that's just a nice little succinct. So Griffith has written in the chat something that's exactly the same, but just a rewriting slightly more succinctly. Okay, but basically the idea is you add up all the characters in the so you pull out each of the characters in the key. The key is a string, remember? So you pull out all those characters, you add them all up, remembering that when you pull a character out, it's actually a number. Okay, it's a 16-bit number. That's how characters are encoded in Java. So it's a 16-bit number. You add them all up, so you get some number, and then you take the integer remainder when you divide by buckets, which is what this is doing here. Okay. Now, there's one much better way of doing it than what anyone has said here, and I told you about it just a few minutes ago. See if you can remember what it is. Okay, there's something else, something you're all missing. It's not much better. It's just simpler. What else is there? There's another way of doing this, folks. Can anyone guess? There's one more. You've just forgotten. Yep, you've all forgotten. Java has what? What does Java have? Java gives us something to make this way easier. Hash code. Yeah, great. Hash code. Okay, we can do that. Will that work? Is there anything wrong with what I just written? Let's run it. Let's just run it. Hopefully you can tell by my tone that I think there is something wrong with this, but I'm going to run it anyway and see what happens. Okay, bang, it didn't work. Let's go back to our IntelliJ. Okay, and what's happened? Ooh, that's interesting. It behaved very badly, worse than what it should have. Up there, that's what I wanted to see here. Okay. Yeah. Oh, okay. Sorry. Yes, that's the first thing. Absolutely. Need to use that. So let's do that. Okay. Now remember what is that there? That's not modulus, is it? It's integer remainder. Let's see what happens now. Okay. Has that fixed it? Let's see. Let's run it. Bang. Didn't work either. Okay. What's going on? What's wrong with it? Can anyone guess what's wrong? Here it is. Modulo, this is the very first lecture, one of the very first lectures, I tried to give you the distinction between integer remainder and modulo. Integer remainder can give you a negative number, okay? Modulo won't. So what we need to do here is we need to take the absolute value of the answer, okay? So we can do that by going math. This is something you really need to remember because you're going to run into this plenty of times. Math.abs, like that. Sorry. put the bracket in the wrong place there and get rid of this bracket there. Okay, so now what we've done is we've taken the hash code which Java gives us for every object. So each string is an object in Java. It has a hash code. We've taken its hash code, and we've done an integer remainder by the number of buckets, and then we've taken the absolute value to make sure we deal with negative numbers. Okay, we have to do that because the integer remainder could be negative because the hash code could be negative. Okay, hash codes are a 32-bit number which could be positive or negative. Okay, so that's why we need to do this. And we could have done the abs of the hash code or the abs of the hash code integer remainder buckets. Either would work just fine. Let's have a look at it. Let's see if it works. Hooray, it worked. Okay, and there's the orange one. Orange is the hash code, and there's the family names, given names. Purple was when we added everything up and then took the integer remainder, added up all the characters, and then the dictionary. Then the top one there is where we just took the first character. Okay, so what you see here is these two here are actually, if you look at them, we're looking at here just qualitatively, just eyeballing them. If you just eyeball those, I think you'd probably agree that they're pretty equal. Okay, one way to get a sense of it is where is that grey bar at in terms of the overall y-axis, and if ideally it's right near the top, like you see here. You can see here it's about there, which is it's slightly better than that, but not much different. Okay, and maybe that one's slightly better than that one. Okay, but you can see here these are good hashes. That's not a great hash. Okay, these are not a great hash. You see a very uneven distribution of stuff here, much more even distribution here. And why can anyone guess why the dictionary might give a better result than the others? Anyone got a quick guess? You need to understand very, very basic statistics to think of that. Why would this be better than these two? Even when we use the hash code, the Java hash code. Can anyone guess? Think about statistics. Okay. Yeah, exactly. Renee's hit the nail on the head. Much higher sample size. I can't remember how many words are in this dictionary, but from Boggle, you might remember from Boggle, I think it was like 16,000. I can't remember. Yeah, there's something like 16,000 here, and here there's only like 400, just the people in the class, okay? So that's 16,000, that's more like 400, and so the probability of getting them evenly distributed, even when you use a really good hash function, is much worse when you have these small sample size than when you have this big sample size over here. Yeah, spot on, well done. Okay, great, now let's move on, I think we're done with that, and it's time to move on to the next module. Sets. Okay, we're going to very quickly talk about sets, and then we're going to move on and actually implement sets. Okay, so we talked about the key data types that Java offers, and remember we're going to take some of those and we implement them from scratch. And as you might be guessing, we're about to go and implement sets using hashes. Okay, so the set abstract data type. So the set abstract data type corresponds to a mathematical set. You all should know what that means. It's got the fundamental properties. Duplicates are not allowed. So if I have a bowl of fruit, which is a set, then if I say apple, banana, apple, the set contains, there exists apple, there exists banana. There's no concept of counting how many are in there. It's not like there are two apples. There's no concept of counting. It's a question of exists, or contains is the word we actually use. Okay, so set contains apple, set contains banana. There's no concept of two apples and one banana. Okay, there's no concept of count. Okay, order is not preserved in a mathematical set. There are Java set implementations that allow you to put an order, like a set tree in Java, but order is not a property of a set. Okay, so a set may support operations such as create an empty set, add an element to the set, contains, which allows you to check if this thing is in the set, and a remove, which allows you to take something out of the set. Okay, hopefully that's pretty simple and pretty clear, and it's distinct from a list, which is what we did in the previous modules. Okay, we did in A1 and A2 we did lists. Now we're doing sets. Okay, this is the interface we're going to work to. Very, very simple interface, and I've actually gone to code that up already, so we'll in a few minutes I'm going to start coding against that. And it's time for the mini quiz already. Where are we? Okay, there's the mini quiz for A3, and let's keep moving on. Now we're going to go to hash tables. Okay, hash tables. So, so first of all, I'll tell you what a hash table is, and then we'll look at how you can implement a set using a hash table. Okay, and if you remember your the standard Java concrete data types we get, one of them is called a hash set, and it shouldn't be a surprise to you to hear that the hash set is implemented using hashes. In fact, it's implemented using hash tables, and we're going to look at them in detail in a few minutes, because that's exactly what we're going to build from scratch in today's lecture. So what is a hash table? A hash table stores key value pairs. Now you should be familiar with key value pairs in principle, because we looked at key value pairs using the Java API earlier in semester. We looked at, for example, we had the student, we put the student and we added more students to the class, and so we had a set of students, right? And a hash table, and we had maps as well. We looked at maps. Now we're going to build these things up. A hash table is a data structure that stores key value pairs using a hash function to map them into a table. Now, if you've remembered my example of the mail in the residential hall, you'll realize that that hash function and the table is very much like the mail delivery thing. Okay, so if your table had only one thing in it, there's a table of size 1, which is kind of silly, then all the mail goes into one hole. Or in the bar graph, if your bar graph had just one thing in it, then everything goes in there, obviously. Okay, and the hash function maps across all of the entries in the table. Now, when we build things in real life for hash tables, they might have thousands or even millions of entries in them. Okay, in the examples we've been looking at in class, we've been using 10 or 20 and things like that. But in a real world hash table, it might be millions. Okay, so what are the key challenges? Dealing with hash collisions. What's a hash collision? That sounds awful. It's actually really common. It's when multiple things go to the same value, hash to the same value. And you've seen that with our examples. Obviously, with the dictionary, we had 20 buckets, okay, 20 buckets and 16,000 words. So each of those buckets had thousands of words in it, or many hundreds of words in it, okay? And that's a hash collision, meaning multiple things going to the same place, all right? And dealing with load, how to make the table big. How do we know how big to make our table? Okay, the table I just gave you was of size 20. The one I drew on the screen was of size 20. How big should I make that? Should I make it of size 2? Should I make it of size 1,000,000? How do I know? This is a really difficult question. And the answer to it, in theory, is if we know the set, the size of the set, we call it the cardinality. If we know the cardinality of the set that we're going to be dealing with in practice, like when we actually use this thing in practice, then we might want to make the hash table about that big. Okay, but often we don't even know that in advance, because we write this code and we don't actually even know how it's going to be used. Okay, so this makes things a little bit interesting, a little bit difficult, and sometimes we can, as a programmer, actually say, hey, make me a really huge hash table, because I know for this particular application we're going to want a really big one. Okay, and there are two broad approaches. We're only going to look at one of these. We're going to look at separate chaining, which is the first of the two I've listed on the screen here. So the separate chaining, hash table entries are lists. Actually, before I go here, what I want you to think about is how we can implement a set. Okay, let's just back up one moment and think about how we might implement a set. I jumped over this. Let's back up and think, how am I going to implement a set? What data structures could I use? Okay, I've given you a giant clue that a hash table is one. And you also should have seen a clue that a tree is another. We haven't talked about trees much yet, but you've seen that Java has a thing called a tree set. Okay, we've got a hash set and a tree set. So it should be pretty obvious that there are two ways that you might implement it. Now, my question to you, and I want people to write answers in the chat if you can we implement a set using a linked list? Can we do that? Can we implement a set using a linked list? So you know what a set is. That's the thing with the apples, bananas, pineapples, and so forth. And we know what the operations are. We saw that just a moment ago. Here's the operations. We've got to add things to it. We've got to check whether things are contained. So write your answers on the chat if you can, and tell me whether or not you think we can implement this set thing here using a linked list. I've already told you that we can do it using a hash table. We're going to go there in a minute. I've already told you that we can implement it using a tree. Okay, but the question is, can we implement it using a linked list? And someone has said yes. Okay, that's an interesting answer. Anyone else got other opinions? Someone else has said yes. Okay, so we have some yeses. People have said, I think so. Okay, these are actually good answers, right? Because a lot of people would say no, right? But but people here have seen that their actual answer is yes. But okay, so I'll change the question now. I'm now asking a different question. The question is, would it be a good idea to implement a hash table as a set? Would it be a good idea? And if not, why not? Why would you not? Okay, people have already answered that you can, because I asked, is it possible? And they're absolutely right. It is possible to implement your set as a linked list. So if it's not a good idea, then why not? Probably not the most efficient way. Perfect, Linda. Not the most efficient way. Why not? Okay, so let's just think about it. Let's just go through the mental exercise of thinking about implementing this set here using a linked list. Right, so what we're going to do is, if there's a collision, you're going to have to walk through everything. Okay, so let's just think about it. Imagine you've got this set of fruit, okay, and I'm going to add apple. Okay, so I've got a linked list, it's got nothing in it. Now I've added apple. So I've now got one node in my linked list, it's got apple. Okay, and now I'm going to add, and someone else has written here, it's too difficult to check for duplicates. And someone said searching as order n if there's a collision, just for those of you who are watching the recording here. So I want to add an apple. So I add a node to my linked list, which is an apple. Then I want to add a pineapple. Now I've got two things in my linked list, an apple and a pineapple. Then I want to add an orange. Now I've got three things in my linked list with an apple, a pineapple, and an orange. Now someone says add orange. Now what do I need to do before I add that orange? In fact, I need to do it with the others as well. What I need to do is I need to search that list to see if there's already an orange in there before I go and add another orange. Okay, so I go, is this one an orange? No. Is this one an orange? No. Is this one an orange? Oh yes, this one already is an orange. We already have an orange, so therefore we can't add another orange. Okay, so we just leave it. Okay, and then when I say contains, it's the same deal. If I've got, say I've got 5 things in my linked list, 5 different things. Okay, 5 different fruits. You know, apple, orange, pineapple, banana, plum. Okay, and if I want to say, is there an apple in there? Well, it turns out it's pretty quick because it happens by chance to be the first thing in this list. But if I want to say plum, I've got to go here, 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 and here to find out if it's plum. Worse, if I want to look for fig or for apricot, I've got to check everything before I can know for sure that there's no apricot in there. Okay? Well, okay, so that's 5 steps. Big deal. But what if there's a million things in my set? If there's a million in my set, that's going to be ridiculous. Okay? So what I've just explained to you is that, and you've answered me really well on the chat, is that yes, you can implement a set using a linked list, but you wouldn't want to, okay? Because it would be very, very inefficient once your sets start getting big. Because as Adam said, you've got to do order n steps to find out if it contains, and also for add, okay? Because to add, you have to check whether it's already in there, okay? So, and likewise for remove, because you've got to find the thing in there, okay? So this is a bad idea. But what we can do, just like the mail problem, remember with the mail, if you put everything in one box, okay, I've got to search through every item of mail to look to see if there's any for me. Okay, even if I find one, I don't know if there might be 2 for me that day. So it means I've got to search through every single piece of mail to know I've got all my mail. Okay, and then what we did with the pigeonhole is we busted it up, and then suddenly I only have to look through 1/26 as much stuff. Okay, so the process was the same, it was just shorter. Okay, I still have to search through all the stuff in the box for B, but I only had to search through 1/26 on average, about 1/26 as much stuff as if it was just one huge box. Okay, and that is what motivates using a hash set. Okay, so let's just go here. Okay, so separate chaining is when we have in the hash table, we have a linked list. Okay, so looking through the linked list is not a great thing, but if I've broken it up into lots and lots of small linked lists, then maybe this is a really good way to do it. Okay, which is exactly like the pigeonholes for the mail. I've broken it up and made it much more manageable. And if you have sufficient pigeonholes, then the work becomes manageable. Notice that there's a trade-off with implementing it using pigeonholes. Okay, so in principle, the hall could have had 250 pigeonholes, 1 for each person. What's the problem with that? Well, they're actually made of wood, and they put them in the dining hall, and that would have taken up an awful lot of space in the dining hall if there had been 250 things this big. It's 1/10 as much space to make 26 of them. Okay, so that's why you do it. There's a trade-off. It actually costs money to build lots of these pigeonholes, and it looks bad. Okay, so it's much more efficient to just have 26. The same is true in the computer. You could make these things absolutely enormous, but then you're wasting lots of space. Okay, so you got this trade-off between making them too small, and there's a lot of work to be done, or making them too big, and you're wasting lots of stuff. Okay, open addressing says we don't have linked lists at each entry in the hash table, but instead we just go to a point in the hash table, and if it's already filled, we go to another point in the hash table. We're not going to discuss that in this class, so open addressing is not part of our class. We're just going to look at separate chaining. Don't you generally want square root and pigeonholes? I don't know. Someone says, Griffith says that in the chat. I'm not sure if that's the answer. It might be. A good question. I have to think about that. All right, so now let's have a look. And what I've got there is a set of, I've got a set here of fruit, and I'm going to put them in a list. Okay, there you go. So now they're in one linked list. This is the example I gave before about why you wouldn't want to use a linked list. Let's just have a look at it, right? So those are all unique. There's no duplicates in there. Notice that if I say add an apple, we do that. If I add an orange, I've got to look down this linked list to see if there's already an orange in there. And then I'll put the orange on the end. Okay? Now if I add banana, I've got to check first to make sure there's not already banana in there. So I do that, and I'll look through here, and I add my banana. Add a pear, same thing. I've got to check all the elements of the linked list to see if there's already a pear in the set. Okay? And if I want to add an orange, I get through there and I realize the orange is already in there, and I can stop. Add an apricot, I got to go through everything, and eventually I find that there's actually no apricot, so I can add the apricot on the end, and so forth. Okay, so I just go through all that. So this hopefully motivates visually why using a linked list is not a great idea, but it will work. Okay. Now, if I want to do contains, the same thing. If I want to see if orange is in there, I've got to walk through that list. Okay, and there it is. Okay, mango, I've got to walk through this list step by step by step, get through the list, and there's the mango. Okay, and if I want to look through for the fig, I've got to go through this whole list exhaustively, and I get to the very end. Only when I get to the very end do I know for sure that there is no fig in there. Okay, so that's expensive because I go through the whole list to confirm that there is no fig in the list. Okay, so what a hash table does is it says, let's split that list up, just like the pigeonholes in the residential hall. And so now what we've done is we've got a hash here, a very, very simple hash, which is simply hashing on the first layer of the fruit. Notice that this hash here is not very good, because it turns out that fruit, there aren't that many fruit from U to Z, the last quarter of the alphabet. Most of them in the first 3 quarters, so that last bucket of the hash table is empty in this particular case. Okay, I just took the random set of fruit that I happened to choose, and you can see how they've hashed. There's 4 that are from A to F, there are 2 that are from G to M, and there are 4 that are from N to T. All right, so this is how we break that big long linked list and into smaller lists. Now in practice, you probably want to have much more hash to much more lists, so the list would be shorter. Okay, but this just illustrates the point. How does it work? You add an apple and you get this. You add an orange, you put it there. So how are we doing this? Let's just go back, so I didn't explain that. We've got an apple, so we hash it first. We go there, we find there's nothing in the linked list for apple, so we add it. Okay, we look at orange, we hash it, there's nothing there, so we add the orange. We take a banana, we hash it, there is a linked list, we have to check that linked list, we check it, and there's no banana there already, so we add the banana. And we go to the pear, we hash it, we go to this linked list, and we check to see if there's anyone in there, and there isn't a pear already in there, so we can add the pear. And apricot, and so forth. Okay? And we keep doing this, and that's how we build up our hash table. This is a hash table. Okay? What you're seeing here is building up a hash table. Okay, and notice when we want to find an orange, we do this. We want to find a grape, we do this. And we want to find a fig, we hash to the right bucket for the fig. We look through that list, and it's not there. Okay, notice the search is substantially smaller, and if we have even more buckets and even shorter lists, the search to find the fig becomes shorter and shorter and shorter. Okay, that is how a hash table works. So let's get on with this. And now with that, we are ready to go and build one. Now, to make things a little bit quicker, I actually started off by putting the interface in there. This is just the a hash table doesn't necessarily what I illustrated. Someone's asked, can we add the same fruit in the hash table? In that example I just gave in the PowerPoint, I was trying to illustrate a hash set, so I did not want duplicates. Okay, in principle you could have duplicates in there if that was what you wanted to have. And what you know for sure though is all the duplicates would be in the same list. If you wanted to have a data structure which included duplicates and they were sorted like that, then you'd be able to find them quickly, because they would always, if I put 2 bananas in there, if I wanted to allow that, you probably don't, but if you wanted to allow that, then you put those duplicates in that same list. They'd end up in the same bucket, okay? So if I put banana in there twice, then it'd be easy to find because they'd be in the same bucket. But what I was illustrating there was a set, so we weren't allowing them. But getting to your answer, yes, you could in principle have duplicates. Now what we have here is a very simple piece of code which reflects our the data structure we want. And what we're going to do now is we're going to make 2 stubs for this. One is going to be what is it? A hash set, and the other one is going to be a hash tree. A tree set. Yep. Hash set and a tree set. So we're going to make those 2 classes right now. They'll be empty. Then what we're going to do, of course, is write the tests for them, and then we'll go and build a hash set. And then later in A05, we're going to build a tree set. Okay. So let's go on and make those new class here, new Java class. We'll call it a hash set, and add it here, and we're going to give it a type parameter t extends set of t. Okay, just like that. Whoops, of t. Okay, great. And then it says, okay, there's stuff missing, of course. Hey, come on, where's the? I'm looking for the. Where's my little red, there, that's not what I want to do. Trying to make the red thing come up. Why isn't it doing that for me? What's going on? What have I done wrong? How can I make the, does anyone remember how to make this thing show up? Code, analyze. There is a way to do this. This is a keystroke for bringing up the error, but I can't make it come up. Normally you can just hover the mouse there and the red thing comes up. Implement methods, there it is right there, okay? So all my years using IntelliJ, I still have issues occasionally. Option enter for Mac, thank you. What's going on here? Oh, you know what was going on there? I made a mistake. Can you the reason why it wasn't doing what I expected is, let's hover over here and look what the error message is. No interface expected here. What have I done wrong, folks? I've made a real rookie error here. You should have all seen. Anyone see what I did wrong? This should be implements. No, this should be implements. It's an interface, right? That was the problem. Yeah, I wrote extends here instead of implements. Okay, so that's an error you're probably going to make. I made the mistake. You're probably going to make the same mistake. But it's good for you to watch me make mistake, trip over it, and then fix it. Okay, so we've just fixed that. And someone said, Griffith said, wouldn't it also have to search through the keys before searching the buckets? So for smaller sets, it'd be slower. I don't understand what you mean. It would, if the keys hash to the same, bucket, then it's just the same as a set in terms of you still have to go through things. It wouldn't. If you're allowed duplicates, you don't have to search when you do an add. Anyway, that's a digression. I can try and answer that more later, but I don't think I necessarily understand what your question is. Still a little bit hard to multitask here. So now we'll do the tree set, and this time I will try not to make that same mistake. Add it to Git. Now I'll add the type parameter t, which I did do correctly before, but this time I'll type implements. There we go, and then I'll say set t. Okay, oops, didn't, even though I pressed enter, it didn't do that, and now it's still doing this, but that's all right. Oops. Implement the methods. Okay, there we go. Okay. We're in better shape now. So now I've got 2 implementations of the set, and they're both completely empty. We don't have tests yet. We're going to write tests, okay? So let's make another class here, which we'll call set test. I can just right click here, new Java class, set test. Yep, and then off we go. The first thing we'll do is do a test for adds, and then I'll do a test for contains. Now, one little trick that a mistake I made last time I did this last year is that it turns out there's something really odd in Java. You're allowed to add null as an element to a set. So we're going to make sure we include that in our test to make sure that our implementation of sets actually can handle a null. It's a bit bizarre, but you're allowed to do that. If you go and look in the if you go and look at the Java documentation for sets and maps, null is a valid key and a valid value. All right, let's keep moving here. We can say at test, and we'll say public void test add, like that. And then what we're going to do is we're going to say we should have created ourselves a boolean up here. Right, like that, and then we're going to allow that to we're going to use that to allow us to test both tree sets and hash sets. Okay, so by turning that on or off, our test will work against the hash set or the tree set. Okay, but in this class we're just going to do the hash, but in the next unit we're going to do the tree. All right, so now let's say set of string. We're going to use strings again just to make things easy. We could use a different type here, but for the sake of illustration in class, we're just going to use strings. And I want to remind you all again that the tests we're writing in class are really simplistic. Okay, these are really simplistic tests. They're illustrating the point, but they're far from perfect. Okay, it's really hard to write good tests, and that's one of the tasks that you had this week. But writing good tests is a difficult thing to do, and in this class we're just doing it very simplistically, just to give you the idea. So we're creating our set, and it's equal to, depending on whether what hash set is set or not, hash set. If that's true, remember I'm using the ternary operator here with a question mark saying if it's true, then say new hash set, and very important that we choose the right one here. Okay, so make sure we choose ours, not the Java one. There it is. Otherwise, we'll say tree set. Again, important that we choose the right one. What happened there? What's going on? Oh, new. I've got to say new. All right. Okay, another rookie error. Okay. I'm going to keep coding here. I can see you guys having a discussion there. You folks having a discussion there. When you're finished, maybe you can, if you still have a question, let me know. Otherwise, I'll just keep coding. I'm not going to look at the discussion until I've finished typing some of this stuff up. Okay, set dot add. We're going to add stuff to our set and then see if our implementation works correctly. So we're going to add Alice, and then what should be true? Look at our very simple interface here. Remember our really simple interface. It's got add, remove, contains, size, and toString. Okay, so what should be true? Oops, wrong thing here. Okay, there it is. What should be true once we've added this in? A couple of things should be true. Okay, so we can say assert true, and then we can say set dot size equals what? 1. Okay, that should be true. Wrong keystroke, sorry. There we go. Yep. Okay, so we said the size should be 1. We could have also done an assert true at the top here to say that the size would be 0 before we did this, right? Like that. Size is 0. Now the size is 1. And we could say it also must contain Alice, but we don't want to test. In test add, we don't want to assume that contains already works. So we'll just do, we'll just use toString. We're just going to assume size is correct and toString is correct. We won't assume when we're writing this test that contains is also correct. We'll have a separate test for contains, okay? So we're just going to assume, I'll write this up here. Assume that size works and toString works. Right? When I say assume that they work, we're going to test for them. Okay? So we're not testing for the other things. So we're going to, the set should be that. And what should the toString come out of? It just should have Alice in it, right? And then we're going to decide what that sized at toString dot equals, parentheses dot equals. And how do we want to do it? I think we'll just do it like this. It's up to us. How it gets printed out is kind of up to us, but let's just make it like that. Okay, there we are. So that's a test for one thing, and now we need to add more stuff to our set. So let's copy and paste this here, and then we'll add Bob, right? We'll add Bob as well. If we do this, the size should now be 2, right? And it should have Alice and Bob. Should be like that. Can anyone see a problem with this? Can anyone see a problem with the test? I just wrote this line here. I want you to think about that. Try and answer that in the chat if you can. And anyone? And while you're doing that, I'm going to do something else here. I'm going to copy and paste that and make this. This is going to be interesting. So what I've done here, while I'm waiting for you guys to tell me what's wrong with this, what's problematic here, what I've done here is I've duplicated this. Look what I just did here. I've said we've added Alice. We've checked the size is 1. We've checked that the toString just has Alice in it. Now we've added Alice again. The size should still be 1. Yeah, Renee's spot on, right? The order isn't preserved. So in my test here, I've got a problem because I'm assuming an order, and that order isn't guaranteed. That's exactly what I was looking for. Okay, so here I've added Alice twice, and you'll see that I've got the same test twice in a row because it shouldn't have 2 Alices in there. Now I've added Bob, and we've really got to actually put in a condition here because it could come out the other way around. We don't know. Oops. There's nothing about the set interface that says anything about the order. So we have to go like this then. The alternate ordering of this, right? Right, so now I've got both orderings. Size equals 2 is wrong. If I've added Bob, it should still be size 2, right? So when Alice is in there, I've only got size 1. And now I've added Bob, so the size of the set should be 2, Alice and Bob. Okay, so there's 2 things in the set, Alice and Bob. Now, if I add Bob again, it should just be the same, right? So add Bob again, it should stay the same, right? Right? Adding Bob twice should make no difference, okay? We don't have remove working yet in this our assumptions. Our assumptions up here that only size and toString work. So we can't take something away and check if that works. That's not going to be something we can test for here. Okay, but what we can do is we'll just add a third element here. We'll add Cindy. But I'm not going to write it out in full because it's going to take too much of our lecture. This is a good example of what the limitations of working in a lecture. And I just can't sit here writing this stuff while you're all waiting. So I'm just going to get rid of that there. That's true. It has to be equal to 3 when we add Cindy. But it's not going to be... we can write that twice as well. We can add Cindy in twice, and of course it should still be 3 as well. But I'm not going to go and check the toString because it's going to obviously have 8 possibilities, right? So yeah, so here we've got 2, so it's 2 to the power 1, so it should be 4 possibilities are going to be once we have Cindy in there as well. I'm not going to enumerate all those. The other thing I said is we're going to add null. If we add null, it should also be able to. It should also add something to this. So if I add null. Then I should have put it at the start, really, shouldn't I? Well, I'll do a separate. I'll just duplicate this. Okay, I kind of messed up here. It's all right. We can just add another test, make a whole new test here. Test add null. And what I'll do is instead of Alice, I'll just say null. I'll actually add null. Right, like this. Like that. So I'm adding null in there now. And then it should actually, it's up to us how it prints out, but I suggest we just do that. And then if we add null again, it should just be the same. It should be a set of size like that. And then null. And then I just change this to null in all these examples. Right? So null, adding null should just be like adding some other name like Alice. According to what the Java set implementation rules are. Okay, there we are. It should be like that. So now we've got two tests. They're very, very similar. One just adds the null type. Now we're going to do contains, and we're going to pinch this here to see how if we can implement contains correctly. We're going to copy this code to make it easy for ourselves. Because what we'll do is after we've added everything in, that size works, toString works, and contains works. And contains works. There it is. And say test contains. Like that. Okay, so now what we need to be able to do is it should say that it contains, we don't need all this stuff here. We can just say assert true, set.contains Alice, and that should be returning true. And the other thing we can do here is we can test for Bob at this point, and it should say false, right? Because at this point there is no Bob, so it should just say false, right? So we'll say assert false, set contains Bob. There we go. And there we go, we've added that. Okay, and then do the same thing here. After we've added Bob, it should be true that it contains Bob. And we can say, if we want, we can say that it's false, that it contains Cindy, because Cindy hasn't been added yet. It contains Cindy. Right, and then we could grab all the stuff again. And then say, over here, contains true, contains Cindy. Like that. Okay, so now we've got a test for add and contains, and now we're going to do remove, which again we can do by pinching all that other code and just removing some stuff. So this is pretty lazy coding here. But hopefully you're getting the idea. Even if I'm not doing a beautiful job of it, you should be able to get the drift of how we do this. So we do this here. We're going to cut and paste all that stuff and remove. And notice that we keep growing this list of what we're assuming works. And removes works. Okay, so our list of what works is growing. And then do all this stuff here. We've added Alice and so forth. Then what we can do now is, after we've added Alice, we've done all this stuff here, so that's all true. Then what we can do is set.remove, remove Alice. And at this point, we should be back to here, right? And then we can do all this stuff again. So if we've just removed Alice, we should have an empty set. The size is 0, and we can also do a toString. We can do a toString. Hopefully you can keep track of this. Is getting pretty big and monstrous, but here, if we've removed Alice, then this is a good question. What should it do? The set still exists, okay? So if we've removed Alice, the set isn't gone. We've still got a set. It just has nothing in it, okay? So, yeah, we are. So Griffith points out that we're assuming that add works here. Yeah. Oh, well, we're not. Okay, we are, but not in the first one, Griffith. So here we're not assuming that add works. We're testing whether add works. Now and likewise there, but here we are, right? So this is wrong, so I typed this wrong, right? So add, we're assuming, at this point we're assuming add works, not contains, because we're testing contains. And then down here, it should be add and contains, because we're not assuming remove works, we're testing whether remove works. Thank you for catching that. Okay, so when we're testing for remove, we assume that those things are working and they're tested above, okay? So that was badly done on my part. And now, where were we? We're here, we've removed Alice and the size will be 0. We've added Alice back in. The size should be 1. And then if we remove and I said the toString should be a string of nothing, right? Empty string. Okay, but we should still be able to call toString because we didn't make the set go away. We just have a set with nothing in it. Then we added Alice back in. We've added Alice in twice. We've added Bob. But before we do that, let's just check that if we remove Bob, it shouldn't make any difference at all, right? Because we remove something that doesn't exist, it should do nothing, right? Bob's not in there yet, so it should make no difference at all. Okay, so down here we've added Bob and all that stuff's good. Now we're going to do a remove of Bob and a remove of, we can add Cindy in here just for good measure. Add Cindy, or so remove Cindy. That will make no difference because they don't actually exist in the set. So at the moment that's just wasting space. Now we've gone and added Bob, and that all should work. All that stuff works up to here. Now what we're going to do is we're going to remove Bob. Let's just remove Bob, okay? If we remove Bob, we should be back to, then we'll add Bob back in again. Add Bob. We should, if we've removed Bob, then, and remove Cindy, it makes no difference. Okay, we won't remove Alice because it's just going to be too tedious if I do all that stuff. So here I've removed Bob. We had Alice and Bob in our set at that point. Then I've removed Bob, which should have made our set just have Alice in it. I've removed Cindy, which should make no difference at all because Cindy's not there. And then we should have a set of size 1, which has just got Alice in it. Okay, we add Bob back in. It should contain Bob, and it should contain Alice, but not contain Cindy. Finally, we add Cindy, and then we can remove Cindy as well. Bob and Cindy. We can do this, and it should be the same. Okay. So now what I've done is we've put Cindy in there. Now we've removed Bob. We've removed Cindy. Once we remove Bob and Cindy from that set, we should be back down to just Alice. So the size should be 1. And if we add Bob, then we have that, and we add Cindy as well, then we should be back up to. Okay. I think that's enough tests. All right, so now let's run these tests. Well, it's not really enough tests, but it's enough for today's lecture. So now let's run this, and we should fail, right? That's what we always expect. Okay, everything's failed. Now it's time to start writing our code. So let's get on with that. And we're now good to, this is the fun part, we now get to actually build ourselves a hash set. So what's the first thing we should do, folks? Here's our hash set. It's empty, there's nothing here. What should we do first? What do we need? We need a hash table, right? So what does a hash table consist of? Think about that animation. Let's just quickly go back to refresh your memories. There, it's like this thing. You saw it all built up. We're going to have a table of lists, okay? Now, we're going to assume, we're just going to use the regular Java linked list. We're not going to build up our entire linked list from scratch. We're just going to build this part here and just use, for these bits in orange, we're just going to use the regular Java linked list. But for this part here, it will, we've got to build all this stuff up. Okay, so how are we going to do that? Well, we've got to have a hash table. And the first question is, how many buckets in our table? Okay, so someone make a suggestion as to how many we should have in our table. Well, we're going to make it growable. We're going to make we're going to make the number of buckets growable, but we want a starting point. Okay, so what should our starting point be? Should it be like 2,000? Maybe. But what I've said to you before is that when we're building it in class, we want to make it a small number because our tests are very limited. You just saw our test only had 3 elements going into them. It's very, very limited testing. For that reason, it'd be good to test with only a small number as well. Okay, so we're going to start off with just 2 buckets. Okay. Okay, you always want to try and test in a way that's most likely to break what you've done, because the whole point of testing is to try and break stuff to see if it's actually robust. And if you make a test that sort of won't break anything, then that's not a very helpful test. Okay, so now what we're going to do is going to use a linked list. Okay, so then which is our table. So we'll say linked list of type T. We're going to use the regular Java one. Okay, linked list of T. and actually what we're going to do is have a table of them, right? So it's a table of linked lists. So that's our table of linked lists. And what else do we want? We want there's something crucial we need here, folks. If it's a set, there's a very simple other field that we need here to know something about our set. How do we find out the size of this set? I could go and count them all by going to each bucket, then adding up the length of each of the linked lists. I could do that, but it might be easier just to say int elements like that, and then down here for size we can just say return elements. So we'll just have an integer here which just tracks how many things are actually in our set, how many elements there are in our set. Okay, what else do we need for our hash table? Something really important we need. We spent time in the lecture earlier writing these things. What is it? It's a hash function. We need a hash function which will take the element and hash it into the right point in the table. Now, when we wrote them in class earlier, we had integers. We wrote a hash function for integers, and we had a hash function for strings. And that some of our hash functions for strings assume things like char at and so forth, which work for strings. But notice here we've got a generic type T. So what are we going to use to hash against for type T? Anyone? There's a simple answer here. You should all know. This should be at the tip of your tongue. What are we going to hash on? We don't know what type it is, except it's a type T. Yeah, we're going to use hash code. Perfect. Okay, so let's write ourselves a hash function, private int hash and T element, and then take the absolute value in the integer I made it. Perfect. Okay, so we'll do that. We'll say return if the element is null, then we need to be able to do something because null is allowed, right? So if the element is null, then we need to deal with that. So we'll say return element. If it's null, then let's just hash it to, doesn't really matter where we hash it to, but it has to be deterministic, always has to be the same. So we can just say something like, if it's null, we'll just put it in bucket 0, or we can put it in some other bucket, but let's just say 0. And otherwise we'll say math.abs of the integer remainder of the hash code. So element.hashcode, integer remainder, the number of buckets, which is table.length. Okay, so that's our hash function. And then what else do we want to do? We need to make a constructor, which will be public hash set. And that will just, all we need to do is create a table like that. And how many goes in here? To start with, we'll say default buckets, but we might have to grow it, right? Well, we might choose to grow it later, but for the moment, actually, in this class, we're not going to grow it, okay? It's going to be a fixed size, but we're going to change this number after we've tested it if we want, okay? But so we'll just say default buckets, okay? We don't grow it. I misspoke. With a linked list, with an array list, we grow the backing array. Here, we don't grow it. In some sorts of hash tables, you might grow it. In our class, we're not going to do that, okay? All right. Now, we've implemented ourselves the hash function. There it is. We've implemented a constructor which will actually create the table, and then what we need to do is add elements and do a toString. So let's start off with adding an element. And how would we add an element? How do we add an element? Let's remember that slide. There it is. We want to add an element. What do we need to do? Well, we just need to hash to the right bucket and then add something to the linked list. It's as simple as that, right? Hash to the right bucket, add something to the linked list. So let's do that. Okay, so we say, there's lots of ways to do this, but we say int bucket, we often abbreviate bucket like that, equals hash of the element. Bingo. Now we have ourselves a bucket. Okay, because we wrote our hash function up here. So now we know which bucket it is. And then we can just go like this. We can just say table bucket dot add element. Right? Is that good? we're going to add it to the linked list. Is that good, or have I made some mistakes here? Folks, what have I done wrong? I've made a few errors here. I'm hoping you'll kind of notice. I've made at least 2 errors in this code. Can anyone see what the errors are here? Looks like I'm going to have to shut my window over here. Someone started power tools just outside my window. Okay, I'm not accounting for duplicates, absolutely. So what do I need to do? I need to go and look first, as you saw before when I did the this thing here. We had to, before we added cherry, we had to check to see if cherry was anywhere else in the linked list. So I have to find out if the element we want to add is already in that list. There's something else even more fundamental and simple. We need to make sure there actually is a list there. Okay, so let's do that. We'll say the following. We'll say linked list of type T of T LL, that's our linked list, equals table.bucket. Okay, like this. There it is. And then what we're going to do, size is constant here. Okay. Oh well, yeah. Good call, Daniel. We need to do that. We need to update elements somewhere here. We're going to have to do elements dot plus plus. But we only want to do that if we're actually doing an add, because if there's a duplicate, we won't update it. Okay. So now we've got ourselves a linked list. That's our linked list by going there. That could be null, right? So if it's null, if LL is null, that's because no one's done anything yet. The table's empty. So if it's null, we need to create one. Okay. If LL equals null, then we just simply create one. We'll say table bucket. Right, there may be no linked list yet because this is the first time we've come to this this hash table entry. If it's null, then we do that, and we'll say if then we say new linked list like that. Okay, and then what are we going to do? Otherwise, let's have a look inside that thing, and then we'll say if LL. This is what Adam suggested. LL.contains the element. If it doesn't contain, I guess is the way to do it. So what we'll say is just check inside our linked list. Luckily, the Java implementation of linked list has a contains function, right? And then like this. If it does not contain the element, then we do this stuff. And we can abbreviate that now. I think that's it. All right. Any other thoughts on what we need to do here? I think we're just about done. What we haven't done yet is implement the toString method. We've implemented size. That's straightforward. So now we need to do the toString method. And let's have a look at the where is it? Have a look at the PowerPoint. So what we really want to do is something like go here and print all of these guys out, then go here and print these guys out, and so forth. And we want to put commas between them. Okay, so that was the way we wrote our test. Let's go back and look at the test. Set test, here it is, set test. So we want it to come out looking something like this. Okay, so how do we do that? Let's write this toString method. Oops, where is it? Hash set. So what we're going to do is we're going to say we'll create an empty string to start with. String RTN. It's often a good abbreviation for return. You can't say return because that's a keyword. You can't call it return. So we'll call it RTN, which is a nice abbreviation. And we've got an empty string, and then we're going to build stuff up. We're going to add stuff to this. Okay. So the way we're going to have to do it, if you go back to, if you imagine that PowerPoint thing again, we want to do it for each bucket. Okay. We'll check each bucket and add stuff as we go. So we're going to have a for loop here. I equals 0. I is less than table.length, right? And then say I plus plus. Then what we want to do is to walk through the linked list on these, but of course it's only true if the linked list is not empty, not null. So we'll say just like we did up here, we'll say something like this. Just cut and paste. We'll say okay, our linked list is equal to that. Okay, I'm using the index I. Could have called that bucket. Okay, we can let's call it bucket. Okay, so just so it's more obvious what we're doing here, We're going through the buckets. Don't always have to use I. Okay, there we go. So I've used I bucket. So we're going through all the buckets here. Now, if it's null, we don't need to do anything. But if it's not null, if LL is not equal to null, then we want to walk through the elements in that linked list and add them in. But we can do that just using a shortcut, a short form for loop. So TE for the elements in the LL. Okay, so it says for each element E in the linked list, do the following. Add it to, we can just say return TN plus equals E. But that wouldn't work very well, E.toString, I mean. We don't know what type E is, okay? So what we're doing is we're going to force it to be the toString method. Remember, all objects have toString methods. It might be a really ugly one, but they always have a toString method of some kind. Okay, so there's a problem with this though, in that we haven't now put any punctuation, right? So it's just going to jam in all the letters together. So we want to do a little bit better than that. How can we do that? How can we add the punctuation? Well, we want a comma after everything except the last, or another way to think of it is we want a comma and a space before everything except the first. So how do we can easily identify the first here. It's harder to identify the last if with the shortcut for loop. So what we can do is we can say if we're at the beginning, or if we're not at the beginning, if RTN is not equal to empty string, if it's not empty string, then we'll add in the punctuation in front, okay? Which is another way of saying if, right? So, oops. So what that will do, what have I done here? Oh, RTN plus equals. All right, so what we've said is, if we're not the first one, then put in front of us a comma and a space. All right, now I think we've done everything to allow us to test the add. So let's just see if it works. We'll run the test and hopefully add will work. No, add did not work. Great, what's the matter with it? Let's go here. What have we done wrong? Hash set add, line 23, we've got a null. Okay, now, oh, I see. Here's the mistake, right? What we've done is we've created the new linked list, but what I should have done if I want to use this style, continue with this thing, is I need to reset table bucket like that, okay? Because otherwise, in this case, LL will be equal to null, okay? And I think the size is good. All right, so let's just run this. Whoops, run. Still not right. It doesn't equal Alice. String does, so the size is right, but the string does not equal to Alice. What's wrong with the string? Interesting question. Let's just print it out, hey? There's many ways to do this, but let's just, for now, print out the set. See what it says. What did we get here? Ooh, nothing. Okay, so let's just write this to make it really clear. I've just put in a little punctuation mark, little quote, whoops, quote marks. Okay, there it is. And oh, it's not printing out anything. What's going on here? Oh, there it is. There. Oh, it's the set is equal to null when we've added Alice. So that's wrong. Why is it printing out null? Let's have a look here. So it's printing out null. Why is it doing that? Oh, can anyone see? It's very simple. I didn't update this. Okay, I was just returning null all the time, unconditionally. So that would break it for sure. Okay, and now it works. All right, so now let's just get rid of that comment from the thing. So I just forgot to return. I just returned null unconditionally, which is pretty silly. So get rid of that. Where was it? Where did I put that silly print statement? I'll just get rid of that print statement. Okay, great. We've fixed that. So now let's go and add these other bits. Hash set. So we now need to do a remove and a contains. Let's do contains first. Okay, so how are we going to do contains? what we need to do first is go to the bucket, and then we can just check to see if there is a linked list in that bucket to see if what we want is in there. Okay, so what we'll do is we'll first of all hash just like we did up here, and do copy this code here. It contains. All right, so we've taken our element, we've found out which bucket it should belong in if it's there indeed, and then we've got the linked list, which could be null, and if it's not null, then we might still find it. If it is null, then we'll just return false. So we'll say if ll not equal to null, that means there really is one there. Then we'll say, then if we actually found ourselves a linked list, all we need to do now is say return ll.contains element. Right? So we'll return if our linked list, it will return true if it contains it, or false if it doesn't contain it. Okay, now let's run, and hopefully we've got contains working. Oh, yes, but this didn't work. Test add null did not work. All right, what failed? Now I'll look here. Do we need to update size after an element to null? Okay, so I just noticed that this test here failed, okay? Let's go back here, hash set. Okay, so let's think this through. If the element is equal to null, then it should still be able to add it in. That should still work. Oh, I know what we need to do. Let's have a look at what got printed out. I bet a null pointer exception. The two strings is the null pointer exception. Yes. Okay. What's happened here is we've added null as an element to our set, and then we've called null.toString. You can't call toString on a null. Okay. So now what we need to do is change this and say if e is equal to null, then we'll output the string null. Otherwise, we'll call the toString method on e. Okay, so because we're allowed to have nulls in our set, we say if the element that we just found is actually the null element, then we print out null. Otherwise, don't print it out, we add it to the string. Otherwise, we add e.toString. See if that solves the problem. Perfect. We now only need to get remove working. So to do remove, we could, it's very simple. I think it's much the same as what we have here. Let's just cut and paste this. It's just kind of slightly dirty way to do it. Okay, we've hashed. Okay, so we've got the element. We're going to hash and find out which bucket it belongs in. Now we've got the linked list. If it's not equal to null, we need to do something. We don't need to return anything. There's no return from this. If it's not equal to null, then and ll.contains the element. Let's just move this. So what this means is, oops, wrong key again. Sorry, folks. Okay. Mouse problems as well as keyboard problems. Okay. So what we've said here is we've gone to the bucket. We've hashed our element. We've gone to the correct bucket. Now what we've done is we've grabbed the linked list from that bucket. If that linked list was null, then we just go back to the bottom here. We don't do anything because it means there's nothing to remove. Otherwise, if that linked list does contain the element, then what we need to do is two things. Remove the element from the linked list and decrease the number of elements. So ll.remove element like that, and elements minus. With a bit of luck, we're done. Let's see. Fantastic. We're done. So what you're seeing today, folks, is you've dived into the pool of understanding how hash functions work. Hopefully you can remember those examples I gave, starting off with a game with two teams in it for our class. And determinism was a key thing there. We've got those two teams. Then we moved to 10 teams, and we used the UID. Someone suggested we use a UID and it had a hash function. The hash function took in as a key the UID. The function took the UID and took the integer remainder by dividing by the number of teams we wanted, which was 20. The range we had was 0 to 19 for the team numbers. And so that was a hash function. We then went and looked at how you build a set, or what a set means. We looked at applications for hashes as well. And then we implemented a hash set from scratch. Now we've got just enough time to do what I want to do next, which is start on the next unit, and we'll finish this in our next lecture. Notice that our next lecture is actually in about 10 days time, because there's no lecture on this Friday, and there's no lecture on next Monday. Monday is Labor Day. Friday is a break from lectures. So we've got we're going to skip 2 lectures. So we're going to continue this after that. But let's go on and do this here, because this is interesting and it's very, very connected. So it's a good idea to make a start on this now, and then we'll come back to it in about 10 days time. So a tree is another kind of abstract data type. A tree corresponds to an ordered tree in mathematics. An ordered tree. Okay, a tree is defined recursively as nodes. A tree is a node. A node contains a value and a list of trees. No node is duplicated. Okay, so that is the proper definition of a tree, and you can see a picture of a tree right there. There's also a picture of trees there too, but there's a picture of a tree. A binary search tree is a special kind of tree which has the following special properties. Each node has at most 2 subtrees. So how many subtrees could it have? 0, 1, or 2. At most 2 subtrees. A tree may contain key value pairs or just keys. Okay, it could just have a key there, or it can have a key value pair. If it's got keys, we can use it to implement a set. If it's got key value pairs there, then we can use it to implement a map. We'll come to that later. All right. Keys are ordered within the tree. The left subtree contains only keys that are less than the keys node. You could do this the opposite way around. It doesn't really matter, but by convention we'll do it this way. The left subtree contains keys that are less than the node. So each node's got a key, got a key, and everything to the left of it. All the nodes that sit below it to the left will have keys with lower values, and to the right will be the opposite. It'll be ones that are higher than or equal. Okay, so that's the basic idea. Now, I want you to think very carefully about what the relationship is between this and a linked list. Can anyone say on the chat, what's the relationship between this and a linked list? Relationship between a binary search tree and a linked list. There's a fundamental relationship, and you really need to know it. It really becomes quite important. Anyone? What's the relationship between a binary search tree and a linked list? There's something fascinating here, and that is that a binary search tree will be a linked list if they both have nodes, but if you had a binary search tree where everything went down one branch, so you had all these things here, and then everything went down one branch, that is to say each node only had one child, except the last one, which has 0 children, then you've got a linked list. Yeah, a degenerate binary search tree is a linked list. This is really interesting. Okay, and how could you accidentally create this? The way you can accidentally create this is if you add elements to your binary search tree. If you add elements to your binary search tree in order and keep adding them in the order of the keys, what you'll find is each time you're always adding it to the same side. So if every element is progressively larger, or conversely every element's progressively smaller, what you'll do is you'll keep adding stuff to the right, or keep adding stuff to the left. And if you keep doing that and only do that, what you'll end up with is a very strange unbalanced tree which has everything in one line, and that is a linked list. Okay, that's very interesting, because if a binary search tree is balanced, that is, you somehow or other through luck or through design ensure that things are balanced, then the height of the tree is the logarithm base 2 of the number of elements. Okay, that's an interesting property. Whereas if you have a linked list, the height of the tree is equal to the number of elements. There's a big difference between the two, because the time it takes to find something in a tree is equal to the depth of the tree on average. Okay, so on average, if it turned out to degenerate into a linked list, you have to go all the way down to find something. Whereas if it's properly balanced, then you only have to go to the bottom of the tree, which in both cases you're going to the bottom of the tree, but the height of the tree is enormously lower if it's balanced. So let's have a look here. We've got our set of fruit again, and now we're going to put them in a binary search tree like this. So we start off with the fruit. We've got the apple. Okay, it's got one node there, and then we're going to and it could have 2, could have another one off to the left, but just so happens the first thing we put in here was apple. And guess what? We don't have any fruit which are alphabetically lower than an apple. Okay, if we did, If we had an aardvark, then it would go on the left of the apple, but we don't. So we've only got apple there sitting at only one child, which comes off on the right. Okay. The next thing we added was orange. Okay. And so forth. Okay. And that's how the tree gets formed. So the shape of this tree, which is a slightly odd shape, is a function of the order in which we place these things in here. Now you could go and reshape the tree by reorganizing all the elements in the tree, but this is the way they come out if you just grow the tree as the elements arrive and you follow that rule of everything with a higher value is on the right and a lower value is on the left. Okay, let's have a look at this. So we add the apple. There's nothing there, so the apple goes straight there. Okay, so we've got a node. It's got a value. So it's got a key. The key is called apple, and that's it. Very simple tree. If we add orange, we say, oh, orange should go to the right of the apple. So we'll put it there because orange is greater than A. O is greater than A, so we put it to the right. Now we're going to add a banana, and a banana is greater than the apple also. But when we get to the orange, there, oh, that's actually less than the orange. So it should go to the left of the orange. So it's the right of the apple, but to the left of the orange. And now we add the pear, and the pear goes to the right of the orange because P comes after O in the alphabet. Apricot. And the apricot goes to the right of the apple because APR is later in the alphabet than APP. So it goes to the right of the apple, but then you get to orange, you go and realize it needs to go to the left of orange. You get to banana and realize it needs to go to the left of banana. So apricot sits out there. And peach goes out there, mango, and so forth, following the same rule that you always put them in the right place. Now, what you need to notice is because we've got a very clear rule for where everything goes, it means that we can easily find things because we know exactly where it will be if it's in there, okay? Because we can search for it. We can search for it very easily now if we always follow this rule. If you put them in there randomly, you'd have to go to every single node to find out whether or not the thing you wanted was there. But if you follow this rule of everything with a small letter going to the left and everything with a greater going to the right, greater than or equal going to the right, then you have this behavior here. So we add cherry, and we keep going like this until we've got all our fruit in here. And we've got the same set of fruit here as in the hash table example I showed you earlier, but you can see now the data is organized very differently. It's organized in a tree rather than in a hash table. Okay, now if you want to see if it contains orange, you walk the tree. You start off at the first node and you say, oh, it's not apple, but if it's in here, it must be to the right of apple. So I'll go to the right. Oh, look, lo and behold, you found the one with the key orange, and there it is. Look for grape, and you have to walk through that tree, and eventually you find grape. And the way you walk through the trees, you say, is it greater than or less than apple? Yes, it's greater than, so you go to the right. It's less than orange, so you go to the left. It's greater than banana, so you go to the right. It's less than mango, so you go to the left. It's greater than cherry, so you go to the right. Okay, and then fig. Now fig, you walk all the way down to there, and then you discover there is no F. Okay, so let's just walk through this again. So for fig, F is greater than A, so it's to the right. F is less than O, so it's to the left. F is greater than B, so it's to the right. F is less than M, so it's to the left. F is greater than C, so it's to the right. And then you get to grape, and it must be to the FG, so it must be to the left of grape, but there is no left. Okay, therefore you know that fig is not in this tree. Okay, time for the mini quiz. I didn't actually have the mini quiz here. The mini quiz is, oh yes I do. It's here, it's right here. I'll publish that poll. Okay, we're not going to write any code now. We're going to write the code for the A5 on the Friday week. That's in about 10 days time. And instead what we're going to do is move on to our bio. And we've got a great bio here. Hopefully you've heard of Ada Lovelace. Very interesting lady. There's a lot written about her. You can read, there's a number of good books. I encourage you, if you like reading, if you're the literary type, have a look. Some of you will know that she's got an interesting connection with literature. Actually, she's the daughter of Lord Byron. And Ada is also the name of an important programming language. And that language is actually named after Ada Lovelace. And what she is credited with is really, really interesting. She knew a guy called Babbage who invented one of the first computers, and what she did is worked out how to program it. And so she was arguably the first programmer of a computer. So one of the really important historical figures in computer science, and she was a really interesting lady. It's I strongly encourage you to read up on Lovelace if you like history at all, and obviously as a computer scientist, if you like history, you definitely should read this. Very interesting person. With that, I'll finish up. enjoy your break. You get an extra break, so no lecture on Friday, no lecture on Monday because it's a public holiday, and I'll see you in Friday in about 10 days' time. Have a great week, and I'll catch you later.